He failed 11 times before the 12th attempt worked. 11 separate designs built by hand in a blacksmith shop in Waterville, Maine, each one tested in the snow, each one failing in a different way. 11 attempts that consumed 8 years of his life and nearly $5,000, a fortune for a working man at the turn of the 20th century. Money he didn't have, money he borrowed against his shop, against his reputation, against his family's security. And everyone told him to quit. His wife, his neighbors, the business community, they all said the same thing. It's impossible. It can't be done. You're wasting your time and your money. Give it up. But Alvin Lombard didn't quit. He built a 12th prototype, and that one worked. And the principle he invented, the continuous track system that allowed a machine to distribute its weight and float over snow, became the foundation for every tank track, every bulldozer track, every tracked vehicle ever built. The British War Office, looking for a solution to trench warfare in World War I, studied Lombard's patents, scaled up his design, armored it, weaponized it, and created the tank. And Lombard, the blacksmith from Maine who just wanted to move logs over snow, never knew that his invention had changed warfare forever. He died in 1937, thinking of himself as a man who had solved a logging problem. This is the story of Alvin Lombard's failures, the 11 attempts that didn't work, the breakthrough that did, and the legacy that he never lived to see. Let's start with the problem, because understanding what Lombard was trying to solve explains why the solution was so difficult, and why 11 failures happened before success. Maine in the 1890s was a logging state. The forests of white pine and spruce were being cut, and the timber had to be moved from the cutting sites to the rivers, where it would be floated to the mills in the spring. The cutting happened in winter, when the ground was frozen and the logs could be skidded on snow. But moving the logs, hauling them from the forest to the river landings, was done with horse teams or ox teams pulling sleds. And the animals were dying. The conditions were brutal. Deep snow, sub-zero temperatures, heavy loads. A team of 10 or 12 horses pulling a sled loaded with logs would labor through the snow, the animals sinking, struggling, exhausting themselves. Many died from overwork, from cold, from injuries sustained when they broke through ice or stumbled in the snow. The economic cost was staggering. A good draft horse cost $100 to $150, and a logging operation could lose 30, 40, 50 horses in a single winter. The companies were desperate for an alternative, but no one had found one that worked. Bigger sleds just required more horses. Better roads helped, but were expensive and still depended on animals. What was needed was a mechanical solution, something that could operate in winter conditions, that could haul heavy loads over snow without sinking, without exhausting itself, without dying. Alvin Orlando Lombard was born in 1856 in Springfield, Maine. He wasn't an engineer. He had no formal technical education beyond what he'd learned as an apprentice, but he was a machinist and a blacksmith, skilled in working with metal, building and repairing steam engines, fabricating parts. He ran a shop in Waterville doing general work, and he had a reputation as a capable, reliable craftsman. He was also stubborn, confident in his abilities, and drawn to problems. When he heard about the horse mortality issue in the logging camps, he didn't just see a problem. He saw a problem he thought he could solve. Lombard's advantage was his practical experience. He understood steam power, understood mechanical systems, understood materials. His disadvantage was the lack of formal engineering training. He didn't have access to the theoretical knowledge that might have shortened the development process. He would have to learn by building, testing, and failing. Lombard's insight came from observation. Snowshoes work. A man wearing snowshoes can walk on top of snow that would swallow him to his waist in boots. Why? Because the snowshoe distributes his weight over a larger surface area, reducing the ground pressure allowing him to float. Lombard thought, what if you could make a mechanical snowshoe, a continuous surface that moved with the machine, distributing the weight constantly? The concept of a continuous track, an endless belt of connected plates or slats, wasn't entirely new. There had been some attempts, some patents for agricultural machines, but nothing that worked reliably, nothing that had been successfully commercialized. Lombard believed he could succeed where others had failed, and in the mid-1890s he started building prototypes. The first failure, built around 1894, was a steam-powered machine with wooden slats connected by a leather or fabric belt driven by a small steam engine. The concept was sound, but the execution was not. Lombard tested it in his shop, on the floor, and it moved. He tested it in snow, with a light load, and it moved. But the track wouldn't stay aligned. It slipped off the guide wheels, bunched up, stopped moving. The machine was useless. Lombard went back to the shop, analyzed the failure, and concluded that he needed a better guidance system, a way to keep the track aligned and tensioned. The second attempt incorporated guide rails, metal reinforcements, a more robust structure. It worked better. It pulled a light load without the track slipping off. But when Lombard increased the load, testing it with a heavier sled, the track broke. The rivets connecting the slats sheared under the stress, and the track came apart. The lesson was that strength mattered, but so did flexibility. A track that was too weak broke. A track that was too rigid also broke because it couldn't conform to the terrain. The third attempt used heavier links, stronger connections, thicker materials. It was more durable, and it handled heavier loads. But it was too rigid. When the machine went over uneven ground, over a bump or into a depression, the rigid track couldn't conform, and it broke. Lombard also injured his hand during one of the tests when a link failed and snapped, catching his fingers. The injury was minor, but it was a reminder that the machine was dangerous, that failure had consequences beyond just wasted time and money. The lesson from the third failure was that flexibility was required. The track had to be strong enough to carry the load, but flexible enough to conform to uneven terrain. The fourth attempt incorporated flexible joints, articulated links that could bend and twist. The track could now handle rough ground without breaking. Lombard was encouraged, but the fourth attempt failed for a different reason. It bogged down in soft snow. The machine sank, the tracks dug in, and the engine didn't have enough power to pull itself out. The flotation, the weight distribution that was supposed to be the whole point, was still inadequate. The machine weighed too much for the surface area of the tracks, and it sank. By the fourth failure, Lombard had spent roughly $1,200, equivalent to about $45,000 today. He was using his shop's income to fund the project, and the financial strain was beginning to show. His wife was concerned. The neighbors were starting to talk. But Lombard was convinced that the solution was close, that the next attempt would work. The fifth attempt used wider tracks, increasing the surface area, improving flotation. The machine no longer sank in soft snow. It floated, just as Lombard had envisioned. But it couldn't steer. The machine would go in a straight line, but turning was impossible. The tracks moved at the same speed, and without a way to slow one track relative to the other, the machine couldn't turn. It was a breakthrough in flotation, but a failure in maneuverability. The lesson was that steering required differential control, the ability to vary the speed of the tracks independently. After 5 failures, Lombard had been working on the project for 3 or 4 years. The cumulative cost was approaching $1,500. His reputation in the community was shifting from capable blacksmith to eccentric obsessive. Some neighbors mocked him openly. Others were sympathetic but skeptical. And his family, while supportive, was increasingly worried about the financial and social costs of his obsession. But Lombard didn't quit. He was at a crisis point, financially and personally. But he also believed, with a conviction that bordered on delusion, that he was close. He had solved flotation. He had solved track durability, mostly. The remaining problems, steering and power, were solvable. He mortgaged his shop to raise more money, and he continued. The sixth attempt incorporated independent track control, a primitive differential system that allowed one track to be slowed or stopped while the other continued. The machine could turn. Steering was no longer a problem, but the power was insufficient. The boiler was too small, the steam capacity too low, and the machine couldn't pull the loads that a commercial logging operation would require. The seventh attempt used a larger boiler, more steam capacity, more power. The machine pulled heavy loads without difficulty. It steered well, but the tracks wore out quickly. The materials degraded under the stress and the abrasion, and after a few hours of operation, the links were damaged, the connections loose, the track failing. The lesson was that material choice mattered. Durability had to be engineered in, and that required better materials, better construction, and more money. The eighth attempt used better materials, heat-treated steel, more robust construction. The durability improved significantly. The machine worked, and it worked reliably. But the cost was too high. The materials and the labor required to build the machine at the level of quality needed for durability made it economically unviable. A machine that cost more to build than the value it provided to the logging companies would never be adopted. Lombard had built a machine that worked, but that no one could afford. The ninth attempt was an effort to reduce costs. Lombard used cheaper materials, simplified the construction, cut corners where he thought he could. The machine was affordable, but it was back to the durability problems. The cheaper materials wore out, the simplified construction introduced weak points, and the machine failed after limited use. The lesson, painful and expensive, was that you couldn't sacrifice quality for cost. There was a balance, a threshold, and Lombard hadn't found it yet. The 10th attempt was a balance attempt, mid-grade materials, a design that tried to optimize for both durability and cost. It was promising. The machine worked well initially, and Lombard thought he finally had it. But after 10 hours of operation, the axle broke. A catastrophic failure, sudden and complete. The stress calculations had been wrong. There was a structural weakness that hadn't been apparent until the machine was pushed. The lesson was that engineering, real engineering, required precision, calculations, knowledge that Lombard, working by intuition and experience, didn't have. The 11th attempt incorporated reinforced structure, better calculations, lessons from all the previous failures. The machine worked for days. It pulled heavy loads, it steered, it floated, it was durable. Lombard was close, closer than he'd ever been, but the track still had a tendency to shed, to slip off the guide wheels, especially on sharp turns. The guide system, the mechanism that kept the track aligned, was still imperfect. One piece of the puzzle remained. By this point, it was 1900 or 1901. Lombard had been working on the project for 7 or 8 years. He had spent roughly $5,000, equivalent to about $150,000 today. His shop was mortgaged, his health was suffering. He was aging, worn down by the effort and the stress. His wife was barely tolerating the obsession. The community had mostly dismissed him. He had no backers, no investors, no support beyond his own stubborn refusal to quit. And he built a 12th prototype. The change between the 11th attempt and the 12th was specific and, in retrospect, obvious. Lombard redesigned the guide and idler wheel system, the wheels that the track ran over and that kept it aligned. He added a track tension adjustment mechanism, a way to keep the track tight and prevent it from slipping off. It was a refinement, not a revolution, but it was the refinement that mattered. The 12th prototype was built carefully, using all the lessons from the previous 11 failures. Every component was thought through, tested, refined. Lombard built it in the winter of 1900 to 1901, and when it was ready, he took it to the woods near Waterville for a real test. The test was simple. Load a sled with 5 tons of logs, hitch it to the machine, and see if the machine could pull it over snow. The snow conditions were moderate, not the worst that winter could offer, but realistic. Lombard fired the boiler, built steam pressure, engaged the drive, and the machine moved. The track engaged, the machine moved forward. Steady, no slippage. The flotation was perfect. The machine didn't sink. It floated on top of the snow, distributing its weight, just as Lombard had envisioned 8 years earlier. He steered the machine, turning it in a wide arc, and the track stayed on. The guide system held. The steering was smooth and controlled. He ran the machine for 6 hours, pulling the load, stopping, starting, turning, testing every function, and nothing failed. The track didn't shed. The axle didn't break. The boiler held pressure. The machine worked. Lombard's reaction, as he later described it to associates, was relief more than joy. Relief that the obsession was over, that the solution was real, that he had been right. Vindication. Exhaustion. And the immediate practical thought, now I need to patent this and sell it. Lombard filed for a patent in November of 1901. The patent, U.S. number 674,737, was granted in May of 1901. That's an error in the records as I have them. The patent was granted on May 21st, 1901, covering the continuous track system, the method of propulsion, and the steering mechanism. The patent claims were specific and broad enough to protect the core innovation. Commercial interest was immediate. Logging companies that had heard about Lombard's project, that had dismissed it as a fantasy, now saw a working machine. The first commercial hauler was built in 1902 and sold to a logging company in Maine. The performance was everything Lombard had promised. The hauler replaced a 40-ox team, worked all winter without the losses that animal teams suffered, and hauled more timber more efficiently. Orders flooded in. By 1903, Lombard was building haulers as fast as his shop could produce them. He licensed the design to other manufacturers, and production ramped up. The haulers spread from Maine to the upper Midwest, to Michigan, Wisconsin, Minnesota, and into Canada. By 1910, the Lombard steam log hauler was standard equipment in winter logging operations, and the horse and ox teams that had defined the industry were being retired or sold off. Lombard's vindication was complete. Financial, the debt was paid off, the shop was secure, and he was making money. Social, the mockery turned to respect. The neighbors who had dismissed him now pointed to him as a success. Personal, he had solved the problem. He had been right, and the 8 years of failure had led to success. But the story doesn't end there. It extends in a direction that Lombard never knew about, never could have anticipated. In 1914, World War I began, and by 1915, the Western Front had devolved into trench warfare. The trenches, the mud, the barbed wire, the machine gun nests, created a stalemate. Cavalry was useless. Infantry attacks were suicidal. Artillery could soften defenses, but couldn't break through. The British War Office, searching for a solution, tasked engineers with developing a machine that could cross trenches, crush barbed wire, resist small arms fire, and carry weapons. The machine needed to move over terrain that wheeled vehicles couldn't handle. It needed traction in mud, the ability to cross obstacles, and the weight distribution to avoid bogging down. The engineers studied every available technology, and in their patent search, they found Lombard's 1901 patent for the continuous track system. The principle was exactly what they needed: distribute the weight over a large surface area, reduce ground pressure, maintain traction on soft or uneven ground, and provide the stability to carry a heavy load. The British adapted Lombard's design, scaled it up, armored it, and added weapons. The result was the Mark I tank, deployed in 1916 at the Battle of the Somme. The Mark I used a continuous track system, metal plates connected in an endless loop, running over guide wheels, steered by varying the speed of the tracks. It was Lombard's logging hauler, transformed into a weapon. The acknowledgement of Lombard's contribution was minimal. The British patents cited his work as prior art, but publicly there was no credit given. The development of the tank was portrayed as a British innovation, which it was in terms of the application, but the foundational technology, the continuous track, was Lombard's. After World War I, the tank became a standard military weapon. Every nation developed tanks, and every design used the continuous track principle. The technology spread to civilian applications. The Caterpillar Tractor Company, founded in 1925, built agricultural and construction equipment using continuous tracks. Bulldozers, tractors, excavators, all descended from the same principle that Lombard had invented to move logs over snow. The logging legacy of the Lombard hauler faded. By the 1920s and 30s, trucks and improved roads were replacing the haulers. By the 1950s, the steam log haulers were obsolete, scrapped, or abandoned. The machines that had dominated winter logging for 50 years were gone, and the memory of them faded to niche historical knowledge. A few examples were preserved in museums, but the broader public forgot. The military legacy, by contrast, grew. Tanks in World War II, Korea, Vietnam, every conflict since. Tracked armored personnel carriers, infantry fighting vehicles, self-propelled artillery, all using continuous tracks. The technology is ubiquitous in military applications, and the principle is unchanged from Lombard's original design. Yet Lombard is largely forgotten. Caterpillar is often credited with inventing the continuous track, which is incorrect. Caterpillar refined and commercialized it, but they didn't invent it. The British are credited with inventing the tank, which is correct in terms of the vehicle, but the track system was not their invention. Lombard, the blacksmith from Maine, is the foundational figure, and his name is absent from most histories. Alvin Lombard continued inventing after the success of the steam log hauler. He worked on other projects, other mechanical solutions, none as successful or as impactful as the hauler. He died on June 21, 1937, in Waterville, at the age of 81. His obituary noted his work as an inventor and his contribution to the logging industry, but there was no mention of tanks, no acknowledgement of the military legacy, because Lombard himself didn't know about it. He had died before World War II, before the full military adoption of tracked vehicles. And while the British had used his principle in World War I, the connection was not publicized or widely known. Lombard thought of himself as a man who had solved a logging problem. He had invented a machine that replaced ox teams, that made winter logging more efficient, that saved the logging companies money. He had no idea that his invention had become the foundation for armored warfare, that every tank from World War I to the present day used the principle he had developed in a blacksmith shop to move logs over snow. The irony is profound. Lombard's logging haulers are obsolete, forgotten except by historians and enthusiasts. But his continuous track principle is everywhere. Every military in the world uses it. Every construction site has equipment that uses it. The technology that he invented out of desperation and stubbornness, that took 11 failures and 8 years to perfect, is one of the most important mechanical innovations of the 20th century. And the man who invented it died thinking it was a niche solution to a regional logging problem. The lesson of Lombard's story is not just about persistence, though persistence is central. 11 failures would break most people. The financial cost, the social cost, the personal cost would convince most people to quit. Lombard didn't quit because he believed in the solution, because he couldn't let go of the problem, because quitting would mean that all the previous failures were wasted. The lesson is also about the unpredictability of innovation. Lombard was solving a logging problem. He wasn't thinking about warfare. He wasn't thinking about global impact. He was thinking about snow and logs and ox teams. And the solution he developed, the continuous track, turned out to have applications far beyond what he imagined. The technology was adaptable, scalable, foundational. and the world took it and used it in ways that Lombard never knew. So here's to Alvin Lombard, blacksmith, inventor, stubborn bastard who failed 11 times and succeeded on the 12th. Here's to the 8 years and the $5,000 and the mockery and the doubt. Here's to the wife who tolerated the obsession and the neighbors who thought him insane. Here's to the 11 prototypes that didn't work, each one teaching a lesson, each one bringing him closer. And here's to the 12th, the one that worked, the one that replaced the ox teams and transformed logging and became the blueprint for the tank. Lombard invented the continuous track in 1901 to move logs over snow. The British adapted it in 1916 to break the stalemate of trench warfare. Every tank, every tracked vehicle, every bulldozer, every piece of military and construction equipment that uses tracks owes its existence to a blacksmith in Maine who wanted to solve a logging problem and who refused to quit after 11 failures. He died never knowing. He thought his legacy was logging. His real legacy is on every battlefield, every construction site, every place where a tracked vehicle moves over ground that wheels can't handle. Alvin Lombard invented the tank track. He just didn't know it. And the world, for the most part, still doesn't know it either. That's the final irony. The inventor is forgotten, but the invention is everywhere. 11 failures, 1 success, and a legacy that changed the world.